Good morning. So today I'm going to go ahead and start off today's lesson by answering one of the questions that is on your assignment, because there's one that I feel like you guys may not fully understand because I haven't really gone over this diagram yet. So I'm going to go ahead and go over it because it is one of the questions that I asked. So this is, I don't remember what question it is, but it's the one that has like multiple check boxes where you can check stuff off. That question is talking about what happens when you have points on a circle that pretty much are the same in a line. However, the circles just keep increasing, such as this one. So we have this line right here. All these points are on that line, except they're on three different circles. One is on a very small one, one's on a medium-sized one, and one's on a large one. So the question pretty much is asking what happens to the angular displacement and what happens to the linear displacement. So we're gonna go ahead and check that out right now just so I can show you guys what actually happens to these two quantities. So in moving from line A to line B, what the question is really asking is, with this little circle, let me go ahead and color code them to make that easier for you guys to see. So I'm gonna do one in green, let's do orange, and then I'll do one in, what's this one? This blue. So this blue circle is gonna be circle 1. This orange circle, oh my God, that's horrible. Okay, this orange circle is gonna be circle 2, and then the green one is gonna be circle 3. What we wanna know is for all of these circles, in going from point A to point B, what is the relationship between the angular displacement for all three? And what's the relationship between the linear displacement between all three? So the linear displacement is S, which in the last video, I told you guys S was the arc length. So S for each of them is going to be here. So what I really want you guys to see mostly is that each of these arc lengths is different. Why are they different? They're different because each of these circles has a different radius, right? The small circle has this very small radius right here. The medium circle's radius goes out to here, and then the large circle's radius goes out to here. So we have 3 different radii. And because the radii change for each of these circles, the linear displacement is going to get bigger and bigger as the radius gets bigger and bigger. So linear displacement becomes larger as radius increases. Okay, now what about the angular displacement? What happens to the angular displacement? So I'm trying to think of a way that I can show you that's gonna be good. So let me just go ahead and create an angle right here. Say this angle is 21 degrees. Now, let's say I start to add points here the same way that they're on the circle. Does this angle change? That's the question you should be asking yourself. Does this angle change for each of these different arcs? And your answer should be no. Angle does not change. So I know some people may get confused and say that the angle does change because you're gonna try and measure it from here to here instead of from here to here. The angle stays the same all the time. As long as it's consistent, it stays the same. Now, if I were to widen it over here, say it moves up from here to here to like 30 degrees, then it would change. But within this line and this line, that angle has to stay the same. It does not change. So the angular displacement remains the same for all 3 circles. All right, so hopefully that helped you for that question that I put on your assignment. like I said, I don't remember what number it is, but it's the one where you check multiple boxes. This is how you would solve it just by looking at this circle. Okay, so let's see what's next. I'm looking at my PowerPoint. So guys, if you want to follow along with the PowerPoint while I'm doing this, this is totally fine. You can have your PowerPoint open on the side, just open to Windows on your computer, if you can. If not, I'm pretty much just going through it word for word on here. Okay, so I introduced you guys also to angular velocity and angular acceleration on Tuesday, but I'm just going to go over those two terms again. So angular velocity, I told you guys in the last video that angular velocity was described by the variable omega, okay? And I also told you guys that omega is the same thing as the change in the angular position over the change in time, which pretty much you guys could have come up with this on your own just by knowing that regular velocity is equal to change in displacement over change in time. Angular velocity is change in angular displacement over change in time. So it's pretty much the same thing. And angular acceleration is the Greek letter alpha that I told you guys on Tuesday. It looks like a weird fish. And this is equal to the change in angular displacement over your change in time. And those are two basic formulas that you should know just to be able to solve problems that I'm going to give you over the next couple of weeks. Okay. Hold on, guys. Just looking at these slides really quick just so I can see which information I'm going to leave out. Okay, so I'm also going to give you a couple of our alternative formulas that relate linear variables to their rotational variables. So I'm going to make a chart. And like I said in the last video, my A days probably have this stuff because I went over a lot of this with them before we let out for spring break. But my B days, you probably won't have it. So what I'm going to do is create a chart. And if you guys are taking notes, which I honestly don't know if you are or not, you can go ahead and write down this chart. I did it kind of bad. I'm sorry, just try and make these even. It should be 4 rows and 4 columns. Oh my God, that's horrible. Okay, so in this column, this one should be blank. This should say angular. This one should say linear. And this one should say relationship. So the point of this graph is to be able to relate our angular quantities to our linear quantities via some sort of formula that will be easy for you to, use and find an angular giving a linear or find a linear given an angular. So for this row, I'm going to put displacement. This one's going to be velocity. And this one is going to be acceleration. Okay, so the angular quantity for this is going to be theta. And we know that theta is equal to, let me go back really quick. Sorry, I'm having a mind fart. I believe it's R, wrong way. S over R, that's what it was. Sorry, guys. Where S is going to be your arc length and R is going to be your radius, okay? We also know that omega is equal to theta over time, and alpha is equal to omega over time. You can put the deltas in front of them, it doesn't matter. I'm just gonna simplify it and put them like this. The linear displacements are S, and that is equal to the final minus the initial, which we learned at the beginning, except however, this time we're using S's. It's gonna be the same thing. In kinematics, we used X's, which are still the same thing. For this situation, we're only gonna be using S because we're working with arc length, and arc length is denoted as S, but you can think of it as the same thing as using delta X, same thing. Okay, V is going to be equal to S over T, and A is gonna be equal to V over T. Now, this column is the important one. This is how we're gonna show how these quantities are related to each other. So if you wanna find your linear relationship and you have your angular displacement, all you have to do is multiply your radius times your angular displacement, theta, okay? Velocity, same thing, r omega. Acceleration, same thing, r alpha. And that is how you can find your linear given a angular sort of quantity there. So hopefully this will help you with the last part of the assignment. Let me see if I should keep going or save it for another video. Okay, I'm gonna go ahead and stop here, and then I'm gonna make another video about acceleration and kinematics. So stay tuned for that one.